The International Space Station is a place that's getting us ready to go to Mars in the future. It's also a place where science is being done that's leading to some benefits for people who are on Earth right now. One of those experiments that hopes to make good on that second category is called Advanced Colloids Experiment Microscopy. Dr. Matthew Lynch, who is a principal scientist at Procter & Gamble in Cincinnati, is the principal investigator for ACE-M1. He joins us this morning to talk about his research. Dr. Lynch, your experiment is studying the coarsening of colloids with an eye toward making better and longer-lasting products. I've got to start by asking you to tell us what you're talking about. What's a colloid and what is coarsening?
Thanks, Pat. Great to be with you. Let me just describe just real briefly the problem that we have. So as a company, we make a lot of products that are liquids, Tide, fabric enhancers, for example, shampoos. And if you think about it, we put a lot of small drops, actives, into those liquids. And much in the same way as if we put a beach ball in water, it will pop back up. All the products we make have a tendency to do that as well. So what colloids are they're really very, very, very small particles. I can't see them by eye. You have to put them under a microscope to see them. Imagine that they fit on the head of a pin, say, for example. And what we try to do then is change those little colloidal particles. We put them inside the liquids that we want to, inside the products. And we change the chemistry or the physics on the surface of those colloids to make them attractive. And so the idea is when we put them in those fluids, they assemble up. They form little structures, maybe not unlike a house of cards that we might think about, and holds all of those drops in place. And so those are what colloids are, and they begin to change naturally in time. Those structures change much in the same way as that same analogy. We'd pull the cards out of that house of cards structure, they'll fall down. That becomes problematic for stability of a product. And so fundamentally, we just want to learn about how to structure with colloids and the coarsening, how those change in time to make the products go unstable.
Are you able to learn more about that or something different about that by studying them in weightlessness as opposed to on Earth or even doing a computer simulation?
Yeah, actually, it's really important to do in weightless environments. And the reason is this. If I think about these drops have a tendency to change and move through the fluid very, very fast. And the time scales by which they coarsen, these colloids that are meant to hold them, coarsen is very, very slow. And so on experiments on Earth, everything switches and changes so fast, I can't discover anything about how the colloids coarsen and how they move. That changes in zero gravity. I put them in zero gravity now. The rates by which they separate are very slow. And now I can begin to examine the coarsening process of these small colloidal particles.
Is that really just the gravity itself? Because there's no gravity, the separation is slower?
Exactly. So we basically turn off gravity. Separations are very slow. Now I can begin to understand the coarsening behaviors and processes in our structure, so in our products.
What is it that happens inside the experiment apparatus on the station? What goes on in there, and what are the astronauts doing?
Yeah, so as I told you before, these particles are very, very small. So we do on Earth, we make these mixtures that represent what we find in our products. All of that goes up to the NASA Glenn Research Center, and they put them in little cells, little holders for us. All those are up masked onto station. And then what the astronaut will do at the appropriate time is mix them all up. So imagine I have a bunch of colloids. I'm going to randomize them again to restart an experiment, is what the astronaut kind of puts together for us. And he loads it into a microscope. And these things, again, are so small I can't see them. So we put them in a microscope so then we can begin to visualize how they change over time. All that work is done up at NASA Glenn. We go up, we spend time at Mission Control up there and help them work the experiments and to understand the science going forward from that point on.
So you have the opportunity to talk with them directly, and can they give you feedback at the time? They can't see
actually,
either.
Yeah, so we've done that in the past. We actually call up the station, maybe the last questions, talk to the astronauts directly, and be able to provide some feedback about how they're stirring and how they're mixing and if things are positioned properly. So it's actually a really fun and exciting kind of time to do that, as you might imagine.
Now, have you been able to get results so far, or are you still waiting for samples to come back?
Oh no! All the results come down off station by transmission, and so we've learned a lot of interesting things. Actually, the colloids that we use are kind of mixtures of big and small things. That's kind of replicating a commercial mixture of things that we might actually use, and we find that not all colloids are created equal. So Ones that are a little bit bigger behave a little different than ones that are a little bit smaller. And it's provided us a unique opportunity to start thinking about how we design mixtures of big and small to do the kinds of things that we want.
You're learning about the microscopic behavior of these particles, presumably because that teaches you about how they behave on Earth when there is gravity.
Exactly, exactly. So, in a sense, what we're doing is we can imagine a number of things happen simultaneously, and we're going to remove one of those processes so that we can study the other processes independent of that. All of it happens again on Earth. What causes these colloids to coarsen is thermal energy. That's the heat, and that heat is here on Earth as well as it is up on station as well. So the process is all the same.
And you're doing this with an eye toward building, well, better products. Better in what way?
Exactly. So, well, you think about it this way: we make products that really improve the lives of people, and when they fail, we no longer can improve the lives of people, right? I mean, that's the idea. So, where we have problems is where things separate out. That causes failure, and that causes our inability then to deliver something of value to people. Right?
So, what's your next step in this experiment?
Well, so we have the facilities on station right now. Are fantastic. It gives us some really good insights where to go further. What we really would like to do, though, there's a next set of experiments coming along that use a slightly different facility. Gives us a lot more fidelity in terms of understanding where our particles are, seeing those particles, understanding how they move, measuring three-dimensional structures that we just can't do right now. So we're going to learn from these past experiments. We're going to design other experiments that help us to get better resolution, better fidelity of our experiments and go push that science even further. At the same time, we're working with a group of CASIS, and CASIS is providing us the ability to measure not simply microscopic properties, but also macroscopic properties as well. Kind of connect the big and the small together under the same set of environments with the same systems, and that's going to be very powerful, I think.
You have a timetable for when that new facility, new hardware is going to fly?
I believe it's about 2 years. 2016. I think we're second on the manifest, so we're excited about being able to use that new facility.
Right. Well, good luck as you apply your findings and on the future experiments. And thank you for taking the time to talk with us about it today.
Yeah, it was a pleasure. Thank you so much for having me on.